Let us create the encryption program enc.rb asked in the second problem of project 4. Well, you can in fact find the program enc.rb in your downloaded directory proj4. So let us start the code editor to see the program. And then File, Open, and then this enc.rb. Okay, this is the program enc.rb. As we discussed in the lecture, this part is for preparation. First, prepare the variable to keep code number of the letter A, and then prepare the variable K for the number of shifts. Then here, input a plain text as a string, and then compute its length. Okay. Then the input plain text is stored in the array M, and then its length is stored in the variable length. Then here is a part for creating a ciphertext from the string in M. First, we transform the characters of M to the corresponding code numbers in ASCII, which are stored in this array A. We also prepare the array B for keeping the codes of the created ciphertext. Then, by changing the index I, we go through the array A, creating the ciphertext code for A of I. That is the code of the ith character of the plain text in this for loop. Okay. These ciphertext codes are stored in the array B, here or here. Okay. And then after this for loop, these codes are converted to the characters by this command. Okay. And then these characters as a string is put into this array C. Okay. Finally, the program ends by displaying this C on the screen. Now, let us take a closer look at this for loop. Okay. Consider the ith iteration. Here, the ith character of the plain text, that is M of I, or more precisely its code A of I, is transformed to the encrypted code and stored into B of I. Well, in this program, we already have some statements mainly borrowed from the previous program abc print.rb. So this is for computing the distance of the ith code of A of I from the code of the letter A. And the distance is stored into this variable dist. Then this is for showing the information on the ith character, that is M of I, its code A of I, and then distance, dist. Okay. Then this is the part for doing the actual plus K shift. Recall that the plus K shift is applied only to lowercase English letters. So as before, we use this if statement to check whether the ith character is a lowercase English letter, and if so, compute the shift code into B of I. Okay. Note here we have this else part. Okay. This is for the case where the if condition doesn't hold, which is in our case the case where the ith character is not a lowercase English letter. In this case, we can simply use the same code, this A of I, for B of I, without any change. So let's run this program. For this, start the terminal, and then go into the room for the project 4. That is, type cd cs/proj4. Let's check whether we have the program enc.rb here. ls. Yes, we have this program. So let's execute this program, ruby enc.rb. Then the computer waits for you to input a plain text to be encrypted. So let us type in, for example, Ruby. Okay? Then we have this output. Okay? Let's see it. We get information of each character of the input string at each line. Okay? The first line, that is this one, is for the first character, that is capital R, okay, of the Ruby, okay, and then its code number is 82, and then distance from the letter A is negative 15. This is because this is not a lowercase English letter. The second letter is U, and whose code is 117, and then the distance from A is 20, which is calculated by 117 minus 97, where 97 is the code for the letter A. Okay? The third one is letter B. Its code is 98, and then the distance from A is 1. And the last one is Y, whose code is 121, and then its distance from A is 24. Okay? Then look at the last line. This is the result of this puts command. That is the output. This output C. Okay? So the result is a bit strange. R followed by three A's. Well, we want to get the ciphertext here, but what we got is RAAA. Why? Well, let's go back to the program. Here is the part where we compute B of I, the code of the ciphertext. As we discussed, if this condition doesn't hold, that is, if A of I is not the code of some lowercase letter, then this statement is executed, and then A of I is stored into B of I unchanged. That is why the first character of Ruby, this R, is kept as the first character of this ciphertext, which is correct. On the other hand, for those three characters, U, B, Y, following R, okay, after this capital R, this condition, if condition holds, and then this statement is executed. Then, but here, the code of letter A, code underscore A, is stored into B of I. That is why we got three A's, okay, here, corresponding to each character of U, B, Y. So then now our task is to modify this line, okay, this line, so that the encrypted code is stored into B of I. As we discussed in the lecture, the argument becomes clear by focusing on the distance from the letter A, which is stored in the variable dist. We change this distance and then add it to the code of A to get the encrypted code. Well, for example, why don't we simply add just this distance, dist, to code underscore A. Dist. Okay? And then let's save this modification and run this program. Okay? Then type Ruby, the same string. Okay? Well, we got the same string, Ruby. Well, this may be clear because we didn't change the code here. Okay? So this is the original code. That's why the same string is computed in the array C. which is which is printed out like this. What we really need is to change this dist. Okay, so why don't we simply add k here, because we want to do the k shift. Okay, plus k. How about this? Execute it again with the same input. Okay, so save and execute it with the same input, Ruby. Okay, then this capital R is the same R, and then U is converted to X. Is it correct? Okay, let's consider it. The next to U is V, next is WX. So X is third letter from U. Well, recall that our shift number K is 3. So the character U is correctly shifted to X. How about the next one, E, this one? This corresponds to B, this B, right? And then it again, the third character from B, okay? B, C, D, E, okay? So this E is correct. Unfortunately, however, the letter Y, this Y, the last character of Ruby, is changed to some strange symbol, this vertical line. Let's see. In this case, Y, its distance 24, and by adding 3, the new distance becomes 27, which is go beyond 26. Then its code goes beyond the lowercase English letters, and that is why we had a strange character here. We should have considered the addition in the arithmetic system where 26 is regarded as 0. This is because there are 26 lowercase English letters, so the distance from the letter A is from 0 to 25, and the next to 25, that is 26, must go back to 0. So plus k addition should be in the arithmetic system where 26 is regarded as 0. This type of computation is called modular arithmetic. The modular arithmetic is such a computations where results are always interpreted by wrapping around a certain modulo value, 26 in our situation. Let's consider some examples. In Ruby system, we can execute the program directly. For example, let's type Ruby -e and then puts 1 plus 1. Okay? Then we get 2. This is a result of executing this command, 1 plus 1, which is 2, and then output this 2 on the screen. Okay? So Ruby -e puts this time 24 plus 3 on the modulo 26. Okay? Sorry. Okay? This is 1. Okay? Remember, 24 is the distance of the letter Y from A. And then this computation is add 3 under the modulo 26. And this becomes 1. So the letter with the distance 1 is the letter B. This means Y should be shifted to B. You see? Is it okay? Y. The next to of Y is Z. The next of Z is A. And the next of A is B. So B is indeed the third letter from Y. Now we understand what we should do here. Okay, addition of K under the modulo 26. Let's change it. Oh, oops. Seems like this window is too narrow. Let me widen it. Okay. Okay, so instead of just adding plus K, we should compute the addition under the modulo 26. Okay. Percent 26. This is what we need. Well, some parentheses may not be necessary, but they are quite helpful for us to understand the computation. That is, this part is for computing the new distance, and then we add this new distance to the code of letter A. Okay? So we first compute this new distance after shifting, and then new distance is added to the code of A to get the actual code in ASCII. Let's execute this program. Save it. And then Ruby enc.rb. Then type in Ruby. You see this last line, okay? This is the encryption of this Ruby, okay, correctly, because the capital R is remain the same, and then U is changed to X, B is changed to E, and Y is changed to B, okay, as before, and the Y is changed to B correctly. Okay, so let's try some more example. But before, let us comment out this print command, print statement, because we no longer need this information. Now let's try this one. Okay. And then this time, let's a bit longer message. Okay, for example, meet at Tokyo Zoo at 7 p.m. Okay, this message is encrypted, and then to get this ciphertext. Well, seems like each character is correctly shifted by 3. Please check it later. Now, let's try the whole alphabet. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, V, W, X, Y, Z. The whole alphabet, okay? You see, every character is shifted 3 letters in a cyclic way.